100. Both AgCl and AgI dissolve in NH3. And then we have letter A. What mass of AgI dissolves in 1.0 liters of a 1.0 molarity NH3 solution? Okay, so in order to answer this question, I did have to get a couple of things from the back of the textbook. And it talks about AgI, and I'm mixing this, or it's being dissolved in NH3. So the first thing is they're talking about mass of AgI. And a mass, remember, is in grams. That means that this compound has a selected or a specific solubility. So we just have to find the amount that dissolves. That's basically coming from the molar solubility. So I went in the back of the textbook to find out the solubility product, the KSP, of AgI, and that's 1.5 times 10 to the negative 16th. Now, what is a KSP without its balanced equation? It's nothing. So that's the first thing we're going to do right away. So we just have to write out that formula, or the balanced equation, right? AgI, we always write the compound first for KSPs, and that's going to start as a solid. This will dissociate, right, at equilibrium between its two ions. And it's going to be Ag plus I, right? And remember, Ag is a +1 charge because the iodine is the -1. They're both charges, so this equals aqueous and aqueous. And now I'm just going to drop this KSP value down over here. And maybe I'll just get rid of this. Okay, but now I know that I'm in NH3. So we're also going to be forming another substance, right? And if I have Ag plus and I minus, Ag plus will react and form a complex ion with NH3. So I also went to the back of the book to find out the formation constant, the Kf, of AgNH3 plus, right? I knew this was what the complex ion was because that was the only one in the back that had silver and ammonia. So let's write that out. So now just know that we are forming the complex ion. So that means the complex ion has to be on the right side, and the two components are going to be on the left. Well, this had to be between Ag plus, right? And maybe I'll leave the charges in a little bit, plus the NH3. And together they come together to form Ag NH3 2 plus. Now, just know we just said that Ag was a +1 and ammonia, NH3, is neutral. Just know that for formation constants, all of these are aqueous. Even ammonia, who is not charged. We're not talking about the gaseous ammonia here. And this is aqueous as well. Let's bring down that Kf value. Beauty. Let's get rid of this. Awesome. And now, let's just balance. There were two NH3s, right? Two of them. So I just have to go on the other side and say, okay, I had two of these. Now, the only thing, and maybe I'll just bring this up a little bit, the only thing that I know is that I have 1 molarity of NH3. And it seems like I need to use this component because that's what the question's asking for. But how am I going to get AgI into the same balanced equation as the NH3, right? They have to go together, AgI in NH3. Well, this is when we just add the two equations together. Now, when we do that, remember, things that are on opposite sides will cancel out. So, for example, I have an Ag plus on the right, and I have an Ag plus on the left. So, bye-bye to you, and bye-bye to you. There's nothing else that I could get rid of as far as the equation, so I'm just going to rewrite it. So I have AgI, and that's the solid, and now it's in the same equation as the NH3. Perfect. And this comes to equilibrium, double arrow between the two products, AgNH3, 2 plus, that's aqueous, and the I minus, that's aqueous. But now just remember that when we're adding reactions together, we multiply the K values. So instead of adding these two, I have to multiply them. So 1.5 times 10 to the negative 16th times 1.7 times 10 to the 7th. Let's see what our new K value is. So maybe I will just write K equals 1.7 times 10 to the 7th times 1.5 times 10 to the negative 16th. And 2.55 times 10 to the negative 9th. Well, they did tell me that I'm starting off with 1.0 molarity of NH3. Don't get tempted that you have to times it by 2. Doesn't matter what this is in the balanced equation. This is all that you got. You got 1 molarity of it. So I'm just going to put that I have 1 molarity of this. And maybe I won't put the M value here. And remember, we have a new K value, so that means that we should have a new K expression. And for any K value, remember, it's always products divided by reactants. Keep in mind that the solid, even though we're looking for that, does not go in your K expression. So in this case, we have K equals concentration of products divided by reactants. So we got, let's see. So we have the, oh boy, I think I need a little bit more room here. We got Ag. I still need a little bit more room. That's beautiful. AgNH3 2 plus times I minus, all divided by NH3. And now since I say I have 2 of these, I do have to raise the NH3 to the second. But the thing is, I know what the NH3 concentration is, 1.0. I know what the K value is, 2.55 times 10 to the negative 9th. But what are these two? Well, we don't know them, so we label it as X. So this would be X, and this would be X. Now we could do the whole ICE table, right? To just see, it'd be 1.0 minus X, X and X. However, I'm looking at this K value, and this is 10 to the negative 9th. So chances are, if we check for the, the assumption, the 5% rule, we're gonna be pretty good. So we're just gonna throw in the X values. This is X, and this is X. And let's see what we get. 2.55 times 10 to the negative 9th equals, well, we have these two divided by this 1. So it'd be X times X divided by 1.0. Cross multiply. I mean, do we even have to? Let's just move this up. So I get 2.55 times 10 to the negative 9th equals X squared. Take the square root. And I just realized that this should have been 1 squared, but 1 squared is the same thing as 1. So we're still good when we cross multiplied. But we're always checking. We're always checking for mistakes. Thanks for letting me know. I heard you. Let's see. Okay, so now we have X equals 5.0498. I'm not going to round to the nearest sig figs yet because I'm not at the answer. 5.0498. And that's times 10 to the negative 5th. And that's molarity. Okay. Now, this is what the X values are. However, we care about AgI. And remember, there was only 1 AgI in the beginning. So even though the molarity didn't have anything to do with the K expression, you still have a molarity for AgI. That's the molar solubility. And in this case, we solved for 1X. So the X value is also the molar solubility. So I have 5.0498 times 10 to the negative 5th molarity. This is of AgI. Well, now how do I go from a molarity to a mass, right? A gram. Well, I'm thinking molarity, they gave me liters, right? Molarity equals moles divided by liters. But if you have 1 liter, right? And my molarity is 5.0498 times 10 to the negative fifth. If we just rearrange these, if I'm solving for moles, right? Moles is molarity times liter, but if you're timesing by 1, it's the same number. So this would be equal to 5.0498 times 10 to the negative fifth moles of AgI. And now we're almost there. All we got to do is just convert moles of AgI to grams of AgI. Well, how do I do that? Moles to grams, all we have to do is just times by the molar mass. We don't need to do dimensional analysis. We're too big for that. So, get out the periodic table. I got mine right here. I had to go fetch it. But let's see what we get. AgI. Where is silver? There it is. 107.9 plus 126.9. So all I have to do is just times that number by 234.8. So that times 5.0498 times 10 to the negative fifth. Now I will add my sig figs, 2 sig figs. So 0.012. Yep, that works. And that is your grams of AgI. That's the mass of AgI that will dissolve. There you go. I really hope this helped you out. Let me know in the comments. Love talking to you guys, and I hope you all are doing well. Have an awesome day, and keep studying hard. I'll talk to you later. Bye-bye.